Hi, everybody. Before I started, I'd like to thank Norga for inviting me to come over here. I've never been in Israel before, and it's great. The red wine is fantastic. And Mira for helping me with organizing the trip. Okay, where do I point? A couple of years ago, Ray Huey and co-workers published a paper in Science, and as we all know, the papers in Science are correct, unlike those in Nature. And he called it Are Lizards Toast? And basically the argument is that ectothermic lizards are severely threatened by global warming, especially in the tropics, because they're basically lazy thermoregulators. They simply just get too hot and die. Now the other group of animals which are potentially threatened by climate change, by global warming, are heterothermic endotherms. Those are animals which go into torpor or hibernation, and as everybody knows that hibernation is associated with low temperatures, so if temperature goes up, they of course must be in trouble. And as you can see, I simply stole the title and replaced lizards by hibernators. Now what I'm going to do today is, because they are not thermobiologists here, I give you an introduction to what Torpor is, and thermobiology and diversity, and then I'll talk about what species that express torpor likely, how they deal with climate change, or if they can or not. Okay, now, if you look at organisms on Earth, there are lots of them, and from a diversity point of view, they're extremely complicated. You know that taxonomy is really confusing. If you look at it from a thermobiology point of view, it's really simple. You get ectotherms, which is almost everybody, and endotherms, which is basically birds and mammals for this audience here anyway. And ectotherms are interesting. Ectotherms simply, their body temperature simply follows that of the environment. So it gets cold, they get cold as well. And they have very low metabolic rates, as you can see here. I'll show you 25-gram lizards, because most vertebrates are small. They are little lizards, and birds and mammals are sparrows and bats and mice, not lions and things. But the point is that because they get cold, their metabolic rate goes down as well. So they have a low metabolic rate to start with. If you cool them down, it becomes even lower. And that's very different to endotherms, which is basically us, especially homeothermic endotherms. All you know, we have a constant high body temperature. This is just an example at 37 degrees Celsius. And of course, we have to do something about it. This doesn't stay there by itself, and it's actually quite complicated. So again, I took a 25-gram mammal here for comparison, and you see this is quite a complicated relationship. So they want to keep the temperature stable here, and to do that, they can have a thermoneutral zone, which is very close, so that the difference between inside and outside is very small, so they can have a very low metabolic rate, which is called a basal metabolic rate. This is basically cost of living without thermoregulation. But when it gets hot, they have to put on an air conditioner, sweat, ventilation increase, but most of the time they could go up and down on this line here. So this is basically putting on a heater, thermoregulation. And most small mammals and birds are making heat all the time. It's very, very costly. So if you get the difference here by maybe 10-fold between the minimum here and the minimum there, if you go to 5 degrees Celsius, you're going to get a difference by 100-fold. So a small mammal has to eat 100-fold of what a small reptile has to do at cold temperatures. Of course, they don't eat at low temperatures. Now, you don't have to be a rocket scientist to work out that being here is expensive. You have to eat all the time, and of course, food is not available all the time. And because of that, not all endotherms making heat inside are homeothermic, keeping a constant temperature. Quite a few are heterothermic, changing that temperature. And they can do the same. You can do it. They can keep a constant temperature. They have a resting metabolic rate and a basal metabolic rate. But they also can go into torpor. And when they go into torpor, they thermoconform over a wide temperature range. So body temperature follows ambient temperatures, like in ectotherms. And down that temperature range, the torpor metabolic rate goes down exponentially, also similar to those in ectotherms. But unlike in ectotherms, if you take an ectotherm here and cool it down, they just simply freeze to death eventually. They have a second set point here. This example is 10 degrees Celsius, but it could be a 25 or 0. And in quite a few species, actually at minus. The lowest value is minus 3 degrees Celsius. So they regulate the body temperature here, and of course that costs energy. So they have to increase the metabolic rate when it's very, very cold. So they want to hibernate or go into torpor here at 10 degrees Celsius, because that's where the metabolic rate is very low, and also because their torpor duration, how long they can stay torpid, is very long. You can't see that. And if they thermoregulate down here, it actually becomes very costly. So in fact, it's better to go into torpor at slightly higher temperatures than at slightly lower temperatures. I'll come back to that later on. Now, people always think, oh, torpor is something really rare that occurs. Lots of people think birds don't do it at all, but that's not true at all. Torpor occurs in hummingbirds of the Americas. I think all hummingbirds that have been looked at go into torpor. They're only in America. And they also occur in big things like tawny frogmouths in Europe. That's actually in my backyard. That's the biggest bird known. At the moment, there are nightjar relatives. You have nightjars out in the desert. But it's not even nearly as diverse heterothermy as in mammals. So in mammals, there's huge numbers. So it goes from Etruscan shrews, which are in Israel as well, as a little bat from Southeast Asia, and then to 10 kilos in marmots in Asia and North America, and echidnas. They are egg-laying mammals in Australia. They're quite big. So it's a big body mass range, and you all think of bears. Bears just drop their temperature by 5 degrees. They drop their temperature by 30 or 40 degrees. It's a much, much bigger difference in temperature. And this is just show you that diversity. So heterothermy occurs in all mammalian subclasses, on monotremes, marsupials, pouch mammals, and placentals, which are us and bats and rats and things like this. And there are many, many species, and there are many, many species that I'm showing you here. Okay, now what happens during torpor? Just very briefly, this shows the body temperature measured with transmitters, metabolic rate measured as oxygen consumption at a constant temperature in the lab over time. You see, if you put an animal into the chamber, they go and explore a bit and they go to sleep. That's a nocturnal animal. When it becomes dark, they become active. The body temperature and metabolic rate go up. But then after a while, when they don't find any food, they give up and they go into torpor. And you can see that metabolic rate goes bang. It goes down to very low values. The body temperature goes down. The body temperature pushes the values even lower. And if you can see, they have a very low metabolic rate down here in comparison to up there. And in some species, it can be actually like 1% of basal, like really, really low. It's almost nothing. But of course, this is an example for daily torpor. I didn't really explain that. That comes a little bit later. So those are species which do only very short bouts. Eventually, they have to rewarm because they want to be active again and forage. So what I have to do is they have to push the body temperature from here at about 20 degrees Celsius back up to 35 or 36 degrees Celsius. And that costs. So they have to make an enormous amount of heat, shown here by the increase in metabolic rate. And that's actually viewed as one of the major disadvantages of torpor, that they have to rewarm actively at the end. So if you look at savings, if that's a resting value here, and that's a resting value here, and draw a line, it's basically that area in that circle, which is the daily energy savings. And in daily torpor, it's usually in the order of 20 or 30% reduction in daily energy expenditure. And then if we have to take this away from that saving here. But the animals are, of course, smart. This is done in the lab at constant temperatures. In the wild, they basically play lizards. And this is in Central Australia, in the McDonnell Ranges. And this is actually marsupial. They're called Echinus. And what they do is they go into torpor, just like I showed you before. So they forage in the evening. This is measured in the wild. And I should say here, with transmitters, we now can measure activity and behavior in the wild. This would have been totally impossible just a few years ago. So they run around, then they go into torpor, but instead of warming up actively, they come out and sit on a bit of rock, like on a banana chair here, and then they warm up passively and actually bask during most of the day. And if you go back in the lab and measure how much they save then, they can actually save 80% of the daily energy expenditure if they bask here and if they bask during the day. It's very, very effective. Okay, so this, okay, and the interesting thing is, there's not one pattern of torpor. I sort of mentioned daily torpor before, but actually two patterns have been favored by evolution. And they differ. Some people say they're all the same, but I believe they differ physiologically and ecologically. So one pattern is daily torpor. This is one up here. So those animals have usually large daily temperature fluctuation, and every so often they put in this torpor bout. So most of the time they are at high temperatures. And these species, they usually show no fattening or little fattening, and they usually run around daily and fill up. So they don't need fat because they find a little bit of food, but of course having a low temperature here reduces how much food they need. And then the other pattern is multi-day torpor. In the hibernators, they usually fatten enormously. If you have a skinny hibernator, they don't go into torpor, they refuse to do it. If you have a fat daily heterotherm, they refuse to go into torpor. It's a totally different thing. And they usually don't forage, although some species do a little bit, but I can't go into that. So the hibernation pattern is basically the opposite. Most of the time they're down there at 2 or 5 degrees Celsius, but you notice they always shoot up. So every week or two they have to rewarm. We still don't know why they do it. When they're at low temperatures, something goes wrong physiologically, and they have to warm up to compensate for that. And they have to be very careful that they don't do that too often, because if they store fat, they may run out before the end of the winter. So they usually can rewarm 20 times or thereabouts on fat. Again, just to hammer it in, that the two patterns are very different. So it's just cluster analysis. You can see hibernators here. They're at about, on average, at about 4 or 5 degrees Celsius, very low metabolic rates. Those are daily heterotherms on average at about 18 degrees Celsius. And their metabolic rate is much, much higher. So it's a huge difference between the two. And just because there's some cardiac people yesterday, the lowest values here, like this is the Arctic ground squirrel. That's also for extremophiles. This is at -3 degrees Celsius. This is at -1 or 2. That's probably a bat. When they're in torpor, they have a heart rate of 4 beats per minute. And if you go and poke the bat in half an hour, it's going to have 1,000 beats per minute. This is a huge difference. It's just amazing what they can do. Now to the real questions, are hibernators toast? And that, of course, depends on which pattern you use and where you live. An example here is the mountain pygmy-possum. It's one of the rarest marsupials living in the mountains in southeastern Australia. And there's only about 2,000 left in the wild. Those blue dots here are the current populations on mountain tops. The black dots are from the last ice age. They had a wide distribution range then. So they basically have been pushed up the mountains. They live there on those sky islands. And the reason why they can live there is because they hibernate. So the mountains get covered by snow. This is the snow gum here. And there's boulders under there, and they crawl under there into little balls, and they hibernate away. I think it's the same slide I showed you before, from about April, southern hemisphere, to about September, October. And as I mentioned before, they can do about 20 arousals and about 6 months of hibernation. But it's important, that's only between 2 and 4 degrees Celsius, as they do get under snow. Snow is a thermal blanket and keeps the temperature pretty much stable. And the importance is that how long they stay torpor is very strongly temperature dependent. So if you take a mountain pygmy-possum in the lab, make it hibernating at 12 degrees, they have to rewarm every 2 days. And at 8 degrees, they have to warm every 10 days. At 2 degrees, they have to rewarm, or they can rewarm only every 2 weeks. So they're very, very long torpor bouts, lots of energy savings. If you just drop the temperature by 2 degrees Celsius to 0 degrees Celsius, because you force the animals to thermoregulate, the metabolic rate goes up, and the torpor bout duration goes down. It means they have to rewarm very, very quickly. And from an energetic point of view, that means if they hibernate at 2 degrees Celsius, as under snow, they have to do about 180 days. They have got plenty of energy left. They can use that for reproduction in spring, the extra fat. If they hibernate at 0 degrees Celsius, they fall short. They won't quite make it. And you of ask the question, global warming, why should the temperature drop? It's predicted that in southeastern Australia, precipitation is going to go down, and lack of snow cover most likely will result in a drop in the temperature, so they're exposed to lower temperatures. And this is a prediction, but in fact there's some data coming in from Alaska where global warming results in late snowfalls. And there's one ground squirrel up there, it's called the Arctic ground squirrel. They have extremely fixed hibernation time. They wake up at a certain time period, especially the males, to find females for mating, of course, because they have to get the babies big enough before the next hibernation season. And because of the late snowfall, the males came all out, were running around, no food. The whole population died. So can be very severe. But of course, not all hibernators are strictly seasonal. For example, the eastern pygmy-possum, this lives along the east coast. They're found north and south of Sydney, basically from Brisbane down to Melbourne. And the species fattens enormously. They'd be perfect for doing obesity studies. So if you catch them in the wild, they weigh 20 grams, you just throw some food at them, they go up to 50, 60 grams in no time at all. And what I did is simply fatten up the animal and make it hibernate and measure how long it takes until it burns up the fat. So this is shown here, the data up the top. They're not body temperatures, but movements, which is basically rewarming. And you can see this animal here could do it for over a year, and this one could do it for almost a year. And this was a world record, and it got a lot of media attention, as you can imagine. But the interesting thing is that the arousals, these parts here, required about 85% of the energy, and without them, the pygmy-possums could actually hibernate for 3 years, which is totally ridiculous. And the interesting thing is, too, I haven't published that yet, at 15 degrees, they can still do more than 6 months. So that's a perfect adaptation to simply, if something bad comes along, you can simply sit and wait until the situation gets better. So this is a very potent possibility. Now, heat and drought, both are predicted to go up, and you probably all think that's very, again, has got nothing to do with torpor, because torpor is cold and heat is hot. But not far from here, this is actually Norga's data. She was involved in the study at the Sea of Galilee. There's a bat, and they actually hibernate in hot caves, so in geothermally heated caves. And you can see, instead of going down to 0 degrees Celsius, they hibernate at 22. So this is the body temperatures here, skin temperatures, and they show those periodic rewarmings as well. It's a very similar pattern. And the interesting thing is, too, they also try to minimize water loss. So what they do, they have these funny nose holes. They can open them up when they're breathing, and when they don't breathe, they shut them to minimize the water loss. So they save energy and they save water by doing that. And similarly, back to Australia, with a comparison with the Dead Sea. This is at Sturt National Park, which is sort of on the corner of New South Wales. I don't know if people know where it is, near South Australia and Queensland. We measured bats during a heat wave where the maximum temperature was 48 degrees Celsius. And I went and checked the Dead Sea max is actually 47, so it beats you by 1 degree. And these are the averages for the Dead Sea. So from about the average max in July is about 39 down to about 27 or 28 degrees Celsius or so. So that you can see the temperature fluctuations were higher during that time. And still, the animals went into torpor. Of course, they go into torpor when it's cool in the morning. So this is a torpor right here. There may be another one here, but the data are missing. Sometimes the animals get out of range. But these animals, of course, warm up passively. So they don't want to get hot very quickly. So the ambient temperature goes up here, and you can see the body temperature just lags behind. And the advantage of that is they save energy and water here, and because the delay in body temperature until they reach the critical temperatures where they have to dump water to keep cool, to maintain cool, is so late in the day that they basically prevent it. So they basically ambient temperatures going down again. So it's important for water conservation in the desert heat wave. So water loss in torpor bats can be reduced by 9% of that during normothermia. Oh, I thought this morning everybody was pretty relaxed about times. Okay, and this is reflected in torpor use in a bird, in an Owlet-Nightjar, in the desert as well. In a wet year, they do very little torpor. In a dry year, they do a lot more torpor. Okay, I had to do speed talking here. And it's interesting that this is in relation to this environment. Heterothermic mammals in the Australian deserts are extremely diverse, and I believe it's diverse. They can live there because they use torpor, and probably the same is the case for some of the animals here. Cyclones, I won't have time to talk about that. But I talk about fire. I know it can't be burned here, but you did have fires in Haifa in November 2016. And again, when we first mentioned fire in relation to torpor, people thought we were totally crazy. And then we went and did the work, which was actually very difficult. In Australia, they burn off forests to get rid of twigs and leaves and things like this to prevent really severe fires. And we had to negotiate with national parks and wildlife people, and they eventually agreed for us to do it. So we had before the fire animals, after the fire animals, and the control over the road. And this is what the habitat looked like before the fire and after the fire. And this is the animal. They almost all survived. I show you only female data because they're simpler to explain. Those are the patterns. Essentially no torpor before and the control, and lots of torpor after the fire. Lots of gaps here, which means activity and foraging. No gaps here, very little foraging. So basically what I did is they increased torpor more often, lower temperatures, longer torpor bouts, to compensate for the limit of the reduced foraging activity. And very similar data we have got on echidnas, which are egg-laying mammals. Basically after the fire they show very long bouts. And the interesting thing is they don't change where they live, they stay in the same site. Okay, now this is the rundown. Now of course if you have all these advantages, you should have a survival advantage. And you probably don't know that, but the most or the very large proportion of extinctions in mammals have occurred in Australia over the past 200 years, and most of them in the arid zone. And if you go into the arid zone, it looks like this. There's homeothermic species which don't go into torpor. We have bandicoots, marsupials, we've got 3 extinctions, macropods, kangaroos, 5 extinctions, rodents, Australian rodents don't seem to go into torpor, 8 extinctions, whereas if you look at heterothermics, you get monotremes, no, dasyurids, no, pygmy-possums, no extinctions, and insectivorous bats, no extinctions. So there's a huge difference. If you look worldwide at orders of different mammals, this is totally extinct here, that's homeotherms extinct, this is heterotherms extinct, and if you look at the sum, 57 species versus 4 species. There's a huge difference between the two. So, are hibernators toast? Well, it depends. If you're a strongly seasonal hibernator, especially those living on sky islands up high in mountains, they probably get wiped out. Whereas those which can use it opportunistically, they probably can use it to bridge bottlenecks. These are the people who helped, and money, and thank you for, and sorry I went over. You're asking what test we did?
I'm sorry?
You're asking the test?
I said the numbers of extinctions
Yeah.
by type of animal
Yeah.
was missing a very important number, the denominator. You can say that you have 5 extinctions here and 10 here, but you don't know how many animals there are in the 2 classes. You can't really interpret that number.
All right. Oh, it's switched off. There was another column which I didn't talk about because of shortage in time. It looked at proportion of animals within each group. And if you take just the sum of the proportion, one is 2% and the other one is 20%, or something like this. Can't remember.
So the data look similar when you take into account.
No. There's huge difference. The drawback is that the data are probably not that good. So there's a little bit of, somebody else did a study, a better statistician than I, on Australian mammals, and they found exactly the same.
Okay, I think we will stop now and we'll go for the next one. The next one by Dr.